So it is 10:05. Let's get started. It is my pleasure to introduce Dr. David Manz. Thank you, David, for doing this for us. Today's topic is science of global warming and climate change. And before we get in, or before I pass on the screen to David, it is an honor to introduce you here, David. David has a Bachelor's of Science in Agricultural Engineering, a Master's of Science in Hydrology from College of Engineering, University of Saskatchewan, and a PhD Water Resources Civil Engineering from University of Alberta. He has more than 45 years of experience working as a water wastewater treatment process design engineer, water resources management specialist, climate change specialist, and many more specialists that I don't want to go over right now. And but I will mention that he is being honored or awarded the Alberta Order of Excellence today afternoon. Is that correct, David? Is it today?
Well, actually, I have been awarded it about 3 years ago. They're presenting a platinum Queen Elizabeth II Platinum Medal this afternoon to us.
Okay,
Oh,
so
congratulations.
congratulations. It's a huge honor, and we are very glad to have you here. David has received many honors for his work. So some examples are the Alberta Science and Technology Leadership Foundation Aztec Award for Social Impact, the Association of Professional Engineers and Geoscientists of Alberta, which we all know as a PEGA Project Achievement Award, the Export Achievement Award for Corporate Social Responsibility presented by University of Calgary and Calgary Economic Development, University of Calgary Internationalization Achievement Award, and the Alberta Emerald Foundation's Individual Commitment Award. So without further ado, David, uh, it's a delight to have you here, and we are all very excited to hear from you on this very relevant and important topic. The screen's all yours now.
Thank you very much. Before I start, I'll just make a mention of, you'll see some URLs sprinkled along the presentation. And so those are there to provide an opportunity for delving deeper into any of these topics that I've covered. Anyway, I've been working on this subject here for, I don't know, more than 15, 16 years. And I've come to believe emphatically that climate change is real and it's happening and it's important. Climate changes today are still caused by natural forces, such as changes in Earth's orbit, volcanoes, but the immediate causes are human activities and the release of greenhouse gases and the changes in land use. Now, while natural resources caused very significant climate changes in the past, with catastrophic impacts to all life on Earth, human activities now promise to cause equally significant climate change with equally serious impacts. The difference is that humans can prevent significant climate change from happening at all. It's in our hands. So just a brief history, and I'm going to try and keep it brief, on the science of climate change. And something that is important is that back in 1837, it was really discovered. Climate change as a process was actually discovered, and the Ice Age theory was initiated. That's in the Swiss Alps. 1827, Fourier, he proposed the greenhouse effect, trapping of heat similar to a greenhouse. So that's a long time ago, 200 years. Tyndall, the physics behind the greenhouse effect and what gases would participate in this. And Arrhenius, 1896, identified the role of carbon dioxide. So again, about 120, 130 years ago. And Milankovitch related the ice ages to variations in Earth orbit and the tilting of this axis. This is very controversial, but proven correct. And then in 1961, the Scripps Institute decided to have a carbon dioxide monitoring program on in Hawaii on Mauna Loa volcano. And out of that, the monitoring, and by the way, this monitoring was only possible because of recently developed instrumentation for measuring carbon dioxide concentrations in the atmosphere. And this is very profound. And here we see in this graph, which is now known as the Keeling curve, how the concentration of carbon dioxide has increased over the years and continues to. In about 1967, which is about when I started university, a little year after actually, the first detailed calculation of the greenhouse effect using a computer model. And these guys won a Nobel Prize for this in 21. And Hansen, James Hansen, a very, very famous individual, in 1981 published a study called The Climate Impact of Increasing Atmospheric Carbon Dioxide. And this was presented to the US Congress in 1988. This is a long time. This is 40 years ago. The Intergovernmental Panel on Climate Change, that's a United Nations body, and was organized by the UN Environmental Program and World Meteorological Organization to assess the science related to climate change and report to world governments. And later, the United Nations Framework Convention on Climate Change, UNFCCC, and their job was to take the IPCC information and communicate this to the countries of the world. And as we speak, the Conference of the Parties 27 is now being held in Egypt, and that's organized by the UNFCCC. So the science is taken very, very, very seriously. And people who have tried to communicate this, which is, of course, is the IPCC and United States Vice President Al Gore, were jointly awarded the Nobel Peace Prize for their efforts. However, reaction to these warnings has been less than one would have hoped, and that's just like COVID-19. The problems appear to be that science is complex and difficult to communicate, and the consequences of changing climate have been difficult for the public to relate to. There have been few examples of the impact of climate change, human-caused climate change, that could be pointed to. Natural occurring extreme events have been erroneously attributed to climate change, and this actually damages the credibility of the science. I'm not going to go through this whole paragraph because the dangers of climate change as reported by the IPCC have been challenged by individual organizations and corporations collectively known as climate deniers. And this happens to this very second, which is quite incredible. And I think here, one of the most high-profile deniers is the current president of the World Bank, appointed by none other than Donald Trump. So climate science has to address all of the concerns that are brought up by this constituency, and I think it does so very well. The question is the climate change we are presently experiencing normal for Earth? And to this, we refer to the study of paleontology. And most important, well, part of the most important, are the ice cores that have been drilled into the ice fields of Greenland and Antarctica. And they can take this information and estimate the climate change, particularly temperature and precipitation and many other things for the last almost 1 million years. So these proxy measurements, as they're called, can observe the carbon dioxide in the atmosphere from just 800,000 years ago. And of course, our carbon dioxide levels are quite a bit higher. Similarly, you could use the ice core, but you can also use numerous other proxy measurements just to go back a couple of thousand years. And we can find out all of these different periods which have become part of various controversy. But one thing that is obvious is that the current concentrations of carbon dioxide and the current temperatures match. And this is not normal. Even if we can go back millions of years to establish this. So why is human-caused climate change so important? Well, the IPCC produces these things called assessment reports, AR, and they're on to their sixth one. And that was just last documents to this assessment were just published this year. And there are 3 volumes, really, working groups 1, 2, and 3. And working group 2 here deals with the impacts, adaptation, and vulnerability. And they clearly describe the consequences of not limiting temperature increase to 1.5 degrees by 2021. And none of the consequences are desirable from a perspective of life on Earth. And the changes in the physical environment affect the entire biological community, including humans. Humans might cope, and this is an argument, but biodiversity is threatened, seriously threatened. The International Union for the Conservation of Nature produces this red list, and it indicates that 1 in 4 species are at risk of extinction. It's quite incredible, actually. And this is their latest report, and most life actually is similarly threatened. And humans appear to be the cause for the 6th extinction of life on Earth. Actually, species are disappearing faster than they have ever disappeared on Earth, maybe with the exception of the asteroid that plugged into the Gulf of Mexico and the extinction of the dinosaurs. The observation impacts of recent climate change, and there are a lot, and I'll go through this really quickly, but there are, again, good references to explore, not to mention the guide that I produce. And here we see the increase in greenhouse gas, and it looks like temperature. Ocean acidification. The Arctic, our Arctic is seriously affected. The Arctic and Antarctica and Greenland are warming at rates several times, at least 2 or 3 times that of the rest of the planet. And this is causing shrinking ice, sea ice, loss of permafrost, loss and change of wildlife habitat, impaired transportation, resurgence of territorial claims, and the release of methane and greenhouse gases on loss or glaciers. These are all extremely serious things. Greenland is losing its ice field and glaciers. Antarctica is breaking up. And of course, we're losing our wildlife habitat along with that. The oceans are warming, the sea level is going up, and there is this weakening of the Atlantic meridional overturning current. Really serious. We're losing our coral reefs because of increased temperature and the bleaching. We're changing the thermal habitat of oceans and lakes, and this is causing species to move around. Affects fishing big time. Droughts are more frequent, desertification is expanding, wildfires more frequent, and we're starting to see tropical cyclones. If they're not necessarily more frequent, they are certainly stronger. And our glaciers are disappearing. And as a consequence of everything before, you're getting major habitat change and a challenging biodiversity. And extreme weather events such as the heat dome effects, which we've experienced in Western Canada, more frequent and stronger atmospheric rivers, the flooding in the Fraser Delta, increasing major snowstorms, human health. We won't be able to survive things as simple as hot weather. And the social impacts are terrible. It is aggravating poverty. We're getting mass migrations and war. These are very recent, and they're very important to note. Just this year, we see things like heat wave, drought, and wildfires in Europe and North America, flooding in the United States, heat wave, drought, and wildfires in China, flooding in China, drought in Africa, heat wave and drought in India and Pakistan, flooding in Pakistan, flooding in Brazil, India, Bangladesh, South Korea, Australia, drought in Chile, heat waves in Japan, Hurricane Fiona, Puerto Rico, and Canada. I mean, Canada was seriously hurt. And of course, along comes Hurricane Ian. Then there's the Typhoon Nanmadol, super typhoon, flooding in Nigeria, Arctic warming, and of course, Antarctic warming. All of Earth is affected this year. On what basis do we attribute extreme weather events to climate change? Like, did somebody just decide this was the case? And the field of science is known as extreme weather attribution. And the fifth annual update in this discussion is published by this newsletter, Carbon Brief, and may be found in the URL listed. The study reports that human-caused climate change made 93% of 152 extreme events more likely or more severe, 56% of flooding events, 68% of 81 drought events more likely or more severe. There is an organization which is titled the World Weather Attribution Initiative, and its mandate is to look at previous events and determine if there was a role for climate change in the aftermath of the event. And several of the extreme weather events listed in for 2022 are attributed to human-caused climate change, or at least made worse. Even in today's paper, there are 2 or 3 events that are listed. In this case, of special importance is the flooding in Nigeria. So, with all that said, the question that we have is, what climate change must we adapt to? Like, if we're not going to change it, or if it is changing, what is the situation that we are facing? How do we stop it? If we don't like what we have to adapt it, how do we stop human-caused climate change? And to get there, we have to know the science of climate change. There are no other options. The first thing to understand is that weather is not climate. Weather is a real-time reflection of climate. Weather happens day to day, and the variations of weather can vary quite significantly, but they are varying within the region's climate. In other words, they're expected. So climate is a long-term average. It's very important to understand it as a long-term average, and typically including precipitation and average temperature, averaged over seasons, years, decades. And it's used to describe large regions that are geographically homogeneous. The climate of a region, short and long term, will determine the physical nature of the environment, but also the characteristics of the biosphere, plants, animals, and where we live. So if a climate of a region is known, weather patterns can often be inferred. Now, there are many factors that affect climate, and this graph shows pretty much all of them. It's difficult to say they'd all be there, but there's a lot, and you can't just dive into that without taking a very careful systems approach to the study. And that study has to begin with the Earth's energy budget. And it's incredibly important to understand this. And here we see the incoming solar radiation, 100%. And here we see the outgoing heat radiation. You have 71% here and 29% here. So what's coming in is also leaving. And this conservation of energy is very important part to realize. So this is a stable system because in is equaling out. Earth is neither warming or cooling. If the amount leaving was less than the amount coming in, something is warming and storing. So where do humans fit into this? Well, let's start with the obvious. Humans and greenhouse gas emissions, a biggie. And humans modify the surface of the planet. Farming is a good example, urbanization. And anything that affects the energy budget in one part of it will affect the energy budget all over the place, maybe temporarily or long term. Let's look at the greenhouse gases. This is the one that really gets all the press as it really should be. Now, greenhouse gases are, first of all, a normal part of the Earth's atmosphere, but human activities are continuously adding greenhouse gases to the atmosphere. Now, the greenhouse gases will persist in the atmosphere for a period of time before they disappear. And there are many, well, several greenhouse gases, and each behaves differently. Now, the concentrations of the greenhouse gas in the atmosphere will increase until they're stopped. Okay, makes sense. Or the processes which cause them to disappear participate at a greater rate than the gases being emitted. When we look at greenhouse gases, carbon dioxide, we're really looking at the carbon cycle. We're not going to go through all the details, but this is a pretty good representation of the carbon cycle, and it includes the land, the oceans, and the atmosphere. Were it not for fossil fuels, cement production, and land use changes, this thing would be a perfect balance. What's happening here, what those little red digits indicate, is that the amount of stuff, let's say greenhouse gases, that are going up. This could be something like gigatons per year or something like that. So here you see on the right, gigatons of carbon per year. Now the atmospheric carbon is increasing at the rate of only 4, even though there's 9 going up. Photosynthesis is picking up 3 of that 9, and 2 of it is being absorbed in the ocean at this time. So that's our source. That's the human source of greenhouse gases, primarily. And this is particular relevance to us here. The greenhouse gases of interest, of course, are carbon dioxide, methane. Methane, you're familiar with, is sort of like natural gas, nitrous oxide, and small amounts of others. Nitrous oxide is a product of combustion processes. And these things have been monitored, not for a huge long time, but in this case, it's over 30 years, which isn't bad. And this has largely been constrained by instrumentation, but everything is steadily increasing. So here we see CO2 from fossil fuels, the blue. The orange here is CO2 from land use, and the reddish color is methane. And methane isn't just natural gas. You know, it could be decaying vegetation and a variety of other things. And nitrous oxide is, interestingly, carbon produced by combustion processes and actually agriculture fertilization. So all of them are important, and we can understand these things in light of the carbon cycle. Interesting, and this is important to me, I guess to everybody, the life of carbon dioxide in the atmospheres varies from 300 to 1,000 years. So whatever we put in today, it'll take between 300 and 1,000 years to disappear. That's a long time. But the other things that we need to understand is the source and magnitude of greenhouse gas emissions are known. And by the way, these are all reported by each country, the member country of the United Nations, and sent to the United Nations framework on climate change. I wouldn't have believed this possible, but they do this every year, and every major industry, every government reports this. We know which countries are producing the greenhouse gases as a result. So if you see particular countries being picked on, well, we know who you are. Now, what can confuse things is that water vapor is also a greenhouse gas. And when it condenses in the atmosphere, it forms droplets, which behave like aerosols. They're little particles. Unlike other greenhouse gases, though, water vapor does not accumulate in the atmosphere. What goes up must come down. And it'll come down either as a liquid or a solid precipitate, where it will evaporate, sublimate, or transpire to return to the atmosphere as a gas. And the maximum amount of water vapor in the atmosphere is limited by the temperature of the atmosphere. So the warmer the atmosphere, the more water vapor it can hold. What this is kind of important. It means that when things warm up in the tropics, the atmosphere in the tropics contains more water vapor, and those circulations out of the tropics into our atmospheres, it really bring a lot more water than it would have otherwise. But the circulation of water is known as the hydrologic cycle. So we have the carbon cycle and the hydrologic cycle. So here we see, again, I'm not going to go through this in detail, but we start with the ocean, which is really where you should start when I talk about water. We're getting evaporation. You do get clouds. You don't just get clouds. In this light blue spaces, there's water vapor, a lot of water vapor. And it does behave like a greenhouse gas. And the clouds behave like aerosols. And they move by a process known as advection. And you're going to get precipitation in the form of rain, snow, etc. Where it falls on land, you're going to get the formation of glaciers, and you're going to get runoff and stream flow, groundwater. What goes up comes down in balance. That's exactly how it works. Now, climate models answer the question, what is the effect of adding greenhouse gases to the atmosphere? What is being modeled? And the only way to consider all the factors which determine climate is to use computer-based models, known as climate models. And this was recognized in the mid-60s. It's just too complicated a problem. So people who do this work have divided the climate into these subsystems. Quite a number actually. And it's, like I said, it's come a long way to the 60s. When I was learning how to use a computer, they were just being introduced to universities. And it would have been a real challenge to take on this project. What happens is the Earth is divided into three-dimensional volumes. So there's a horizontal grid, the latitude, and the vertical grid, the longitude. And what happens in each of those little vertical columns, you get the atmosphere is modeled all the way from the troposphere, that's the top of the stratosphere, to the Earth's surface, whether this is land or ocean, and then all the way as far as can go to the bottom of the ocean. And these things are called, this kind of a model is called the atmospheric ocean general circulation models. And then we use another kind of a model called the Earth system model, which I'll talk about in a second. That grid that I showed you, how the Earth is divided into those little volumes, well, initially it was pretty rough, 200 by 300 kilometers. I mean, that's like half of Alberta almost, okay? Well, today it's a lot more refined, and we're getting to 30 kilometers by 30 kilometers. To get finer than this, we have to use really specialized models, which build on the other reports. But this is getting very fine, and you really need supercomputers to do the analysis. In fact, they're barely able to handle all of the considerations. So if we look at what's considered, in the mid-1970s, all that was possible was considering atmosphere, land surface, ocean, and sea ice. And gradually, this is the first assessment report, second, third, fourth, and fifth. And today we're on the sixth right here. And you can see how other factors have been added, like aerosols, carbon cycle, vegetation changes, changes in the chemistry and land ice, like glaciers, ice fields, so on, Antarctica. And to these things we've added deforestation, wildfires, and melting permafrost. It's a lot. So on Earth, a climate model, the atmospheric ocean general circulation model, just included this upper bit. And when the Earth system model was added, which is now, and AR5, we suddenly allow this interaction with the carbon dioxide and either the physical Earth, but including its biogeochemistry and plant ecology and land use. These are very, very, very complicated models. And who are developing these models? Well, there are 50 modeling groups around the world. And Canada has two, one in Guelph and one in Victoria. And these are really internationally well-respected organizations. And they produce models of different types. There are usually variations on a similar theme. And the Intergovernmental Panel on Climate Change has to sort of determine, well, are these models worth looking at or not worth looking at? So what they've done is they've come up with this coupled model intercomparison projects, CMIP. And we're on to the CMIP 6. And only models which sort of pass the mustard, which is quite a few, by the way, it's over 50 for sure, are considered. But they are different, and they approach the simulation in different ways. And but they all look at all the processes that we've shown. And we are particularly interested in how climate responds to changes in greenhouse gases. Standard sets of data are provided the modelers. They simulate the climate and report these to the people reviewing these, the outcome. Now, like I said, the models require supercomputers to run, and they're expensive. They just require a lot of manpower and are really quite expensive computer space. So there's very simpler models have been developed, but they're calibrated using these big models. So how do these models stack up? First of all, I mean, several organizations in the world have put together what they call the observed change in temperature since 1850. That's considered pre-industrial. This is about as far back as we can go. And by the way, this was a consensus report by, I mean, really the top drawer institutions in the world. Now, here we go. Let's not go back here. So what the people have done, this is the IPCC and the people who are reporting to them, they've taken all the models that they've accepted and they've put in the data, which includes simulated human and natural forcing. Of course, the natural and forcing is really solar energy changes and volcanic. Solar is not a big deal. It's not very much. And volcanoes are like here for a few days or weeks typically, and then they disappear. But when they considered both, they got a pretty fair match. The other thing that is important in this graph is you see this shaded sort of tan area here, and here you see the shaded kind of green area. And what that is, that expresses the range in which the different models predicted how the temperatures would change. And the dark brown line is the average of those. And the argument here is, this is called ensemble modeling, is that all of the factors which would affect climate change are considered. And that's very good agreement when both human and natural forces are considered together. So there's a suggestion that the models that the science is well understood. It's understood well enough to be able to use the models to forecast adaptation needs to climate changes and mitigation strategies to limit climate changes. The other fact that people really do have to understand is that the consensus among scientists is very high. 99% at least is that the science is very good and the conclusions are irrefutable. taken to the bank, but lots of other nifty little expressions. Now, how do we use this stuff? And the approach was to develop scenarios of how greenhouse gases would be discharged into the atmosphere to the year 2100. So what happens here? A variety of, let's just call them emission scenarios were developed, by countless individuals, conferences, intense arguments among people in the know, and they developed these scenarios. And here they begin with the words or letters SFSP, and then they have numbers like 1.9, 2.6, 4.5, and so on. And what they do is they tell us how the effect of releasing carbon dioxide into the air, gigatons of CO2 per year. Okay, and for the different, not tell us, they indicate this is the path that is chosen. So if you were looking at, say, SSP3 here, so in 2050, they indicate that in likelihood, you put in 60 gigatons of CO2. Now, similar kind of curves have been produced for methane, nitrous oxide, and sulfur dioxide. Now, sulfur dioxide is more of an aerosol. Now, this table tells us how the global temperature would change with the emissions if we follow each of the scenarios. So if we were to look at, say, this one down here in the bottom, SSP5, and it's called 8.5. There's a little bit of a story behind that 8.5, but for now, who cares? If we look at, well, best estimate, these are all best estimates, no promises. For 21 to 2040, that would include our 2030. You'll get a range from 1.3 to 1.9. And as we go here to 2100, this gets up to 3.3 and 5.7. Conversely, if we go down to SSP1, our best estimate for this period of time is an increase of 1.5, 1.2 to 1.5. Around 2050, best estimate is 1.6. Okay, and they give a range. And the best estimate for 2100 is 1.4 degrees C. We like that. But the likely range is from 1 to 1.8. So how are these models used then? So what we do is we pick a surface temperature of the Earth for the year of interest. That's slide 40. We translate that one. So if we picked SSP1, we would follow the emissions curve for carbon dioxide here. So we go to 2050, we basically find that our net emissions are zero or very close to zero. So this tells us what it needs to be and how that would decrease till we hit 2100. Or you could go to the assessment report, AR6, and you look at climate forecast they report. There's a lot. And there are implications for life on Earth for each of the scenarios. There's just an enormous amount of information here. And there are many other reports. And from this, we select the scenario of interest. We still have to go back here and we pick out the scenario that we're concerned with. And what we're talking about here is the need to create an executable implementation program on a global scale. I mean, I think that's a huge challenge, and you can't overstate it. Now, there's a temptation here to ignore a lot of the climate change stuff. And we end up with discussions on tipping points, domino effects, knock-on effects, all bad. At tipping point, we reach a certain level, say temperature change or concentration of CO2 resulting in temperature change, and suddenly we find out we can't do anything about that situation. And I know the example, the straw that broke the camel's back, is a really good example of a tipping point. or a small change in temperature results in the loss of habitat, the extinction of a plant or animal. 1 degree too much. A domino effect occurs when one process triggers another. Climate change causes drought, which results in loss of crops, water, food, starvation, loss of livelihood, and mass migration. All, all really bad. And by the way, this one here on tipping points, this actually occurs every day. Uh, we live in Alberta. We're familiar with mountains. There are critters that live on the side of these mountains, right on the edge, and they live where the temperature is just right for them. But as the globe warms, this zone moves higher and higher up. Finally, there's no more mountain left, no more habitat, and no more animals. The knock-on effect is like you do this, and something else happens which makes what you did even worse. It's an amplification. So here we see global warming causes sea ice to melt, more open water, more energy absorbed, temperatures increase, more ice melts more rapidly, and so on. From a biological perspective, I mean, we see the polar bear issues, walrus issues that have recently been on the news, or the Svalbard island north of Norway. If global warming reaches 1.5 degrees by 2100, a few of the tipping points that are expected to be reached include collapse of the Greenland ice, collapse of the West Arctic ice sheet. This is major sea level stuff. Die off of tropical reefs, and abrupt thaw of the boreal permafrost, possibly runaway global warming. Now, the IPCC has determined that a 1 to 2 degree temperature increase is really what should be our accepted target to avoid the worst effects. That is SSP-P1, or 1.9. How do we do it? So the approach recommended and endorsed by the nations of the world, and I mean the nations of the world, is net zero. This is a few years ago. It's a big deal. And the emission target for 2050 is net zero, after which the global temperature will not increase past 1.5 degrees by 2100. Now, net zero means that either no greenhouse gases are emitted, or greenhouse gases that are emitted are offset by actions such as tree planting. So you put in 1 unit, so you say that's bad, that's a greenhouse gas, so I'm going to offset that by doing things that subtract carbon dioxide from the atmosphere. So greenhouse gas emissions minus offsets equals 0. That's okay. Maybe. People think it is. It is up to all levels of government, businesses, and entire populations to meet the net zero objective. It's not just turned over to the government. They provide the guidelines. Businesses and the whole population has to buy in. And Canada has a net zero program, and it's accessible on that website. Most countries in the world do. I was going to say every, but that isn't true. What can we do? Well, the first thing we can do is adopt a net zero program. Now, the answers of what we're going to do are apparent in the carbon cycle. Well, we zoom in on fossil fuels in this part of the world, and we deal with it. And some of the ideas we have are to limit the use of fossil fuels, especially coal, and so limit production of carbon dioxide and methane. Now, locally, we are eliminating coal, and that's a big deal. We're limiting the production of greenhouse gases when fossil fuels are used. This is carbon capture and storage. That is also happening here, but many, many, many places around the world. But we are doing it here in Alberta. We're limiting the production of all other greenhouse gases from any source. We're preserving and protecting existing reservoirs of carbon dioxide, such as trees, soil, peat bogs, and oceans. Planting forests. Advice is to eat less meat. A little tricky sometimes. Direct capture of carbon dioxide from the atmosphere with permanent storage. still in the development stage, but happening. Use energy more efficiently, electric vehicles, insulation, many, many others. And what is of particular relevance to this talk is develop and expand in the use of renewable energy, wind, solar, geothermal, wave and tidal, and who knows what else will come along. Little controversy, but not to me, is develop and expand the safe use of nuclear energy. These are small and medium reactors, and the research on fusion is starting to look promising. Right now, nuclear energy is generated by fission, and it produces waste products, which are a real controversy. Fusion doesn't do the same thing. I guess it's important is to educate yourself in the community about the science of climate change. It's real, it's relevant, it can provide guidance. And at the same time, we should be protecting our natural environment. Biodiversity is important and has to be considered. And we can act to limit the impact of climate change. So most important, to recognize that we live in a global community linked by climate and economy. I mean, in the last few years, and especially now with the Russian invasion of Ukraine, we are acutely aware that we live in a global community. We're seeing the negative effects, supply chain confusion, food shortages, loss of energy supply, travel disruption, business disruption, inflation, and recession. These are very significant. They're in the paper every day. The message, global warming and climate change, anywhere on Earth is a threat to everyone on Earth. So you can't just ignore it wherever you are. You have to be part of the effort to, let's say, address the problem. We need to get the public to support net zero. Very significant regulatory, governance, et cetera, are coming into effect. And if the public doesn't support it, these things can't happen. So, brief recap. Climate change was discovered, not invented. It's not a conspiracy. Curiosity-based science determined the physics. It was just pure science. The concentration of carbon dioxide in the atmosphere and the global temperatures are steadily increasing to levels not seen for over 2,000 years, and it's not business as usual. And actually, it's much longer than that. We can go back millions of years. Climate change attributable to human activities is having a very significant negative impact on Earth's physical environment and all life on Earth. And it is a fact we are causing the sixth mass extinction on Earth. And some of the geologists might know about, let's say, at least four that took actually tens of millions or even longer to occur. The impact of the asteroid in the Gulf of Mexico, of course, was relatively quickly. But humanity right now is causing extinction at a very, very rapid rate that has really basically not been seen in the history of this planet. Just several billion years. The climate models exist and they can predict future climate change as a result of our activities. They have identified needs for human adaptation. Not completely good, but getting closer because adaptation has to be very specific. But they can tell us about how to stop it. That's mitigation strategies. So the science of global warming and climate change is important to counter something that is very bad that is happening right now and is within our hands to resolve or to avoid. These are my opinions. All political agendas should support net zero. All levels of governance must be willing to provide regulatory and financial support to achieve net zero. By the way, they do in Canada. This is happening. I'm not sure about this one. The provision of final financial resources for education and research on any aspect of the science of global warming and climate change is critically important. This is dealing with the science, and I just don't mean physical science. I mean biological, social sciences, you name it. Political science, understanding the impacts so that we can adapt to them, and understanding what is happening so we can mitigate. Climate change science is sound. We should support science, and we should stop destructive climate change. Thank you. Thanks for listening.
Thanks, David. Really insightful presentation. We have a question in the chat. Manfred, do you want to say it or?
Yeah, I don't know. I don't know if anybody else, but your voice, Nisha, is coming over very cut. I don't understand what you're saying. Maybe it's my, or there is some interference. Okay. Yeah. So, David, thank you very much for this presentation. I was saying in the chat, if you have heard about this Brazilian fellow who is out there in the media and social media from, by the way, our partner University of São Paulo, Ricardo Felício. He is a climate change denier and mocks those who are working toward remediating it. Have you heard about this fellow or not?
No, I haven't exactly, no, but
okay.
Normal.
Just wondering, because yeah, that's I have been sent videos, of course, from him by, you can imagine, people over the last 4 years here who support a government in Brazil who is not working for climate remediation anyway. I just was wondering if you know that. Thank you.
You're welcome.
Does anybody have questions, comments?
Yes, David, the best layout of the science of climate change I've come across. I had the privilege over 30 years ago of hearing from the, while I was at Environment Canada, the head of atmospheric environment, who later became one of the founders of the International Committee, say that this was coming. But, and since I've heard bits and pieces, ice core analysis, tree rings, including fossil tree rings. But having all of this, are you optimistic?
Strangely enough, I walk on that. But I am optimistic. That's the only choice I think I have. And that's what I believe. I believe, though, in the interim, there's going to be some significant hardships. But we have to deal with it. So I am optimistic.
Yeah. One of the things that I'm optimistic about is the science of heating and cooling, and with heat pumps. I'm sitting in a house that's had a ground source heat pump for over 30 years, and we are net zero. 82% of residential energy is used for heating, cooling, and hot water. My house is heated from our side lawn, and we're totally renewable, net zero plus. And if we would roll out heat pumps such as the Blatchford redevelopment of the the Edmonton Municipal Airport, we have a real crack at 1.5C. But whether we have the smarts to do that.
Well, the problem with addressing the 5-degree target is that they are small potatoes, say, when you compare that to one of the oil sands operations or say the airport. And so people right now, or it appears that the effort is going into the elephant hunting, so to speak. But they're all important, just like you're suggesting. They're all very, very important. And at the individual scale, it just raises awareness of climate change and what they can do to avoid it, and anything that supports those perspectives is very important in my view. Definitely what you're doing.
Hello, I think Bill Eggerson is asking to speak here.
Thank you, Manfred. I did want to make 3 quick comments on David's presentation. I was trained by Al Gore back 20 years ago in his Climate Reality. So your comment about the people not being able to differentiate between climate and weather rings very strong with me, because we used to fight that people said it was cold yesterday, so this global warming crap, it's just BS, and wrong. But I did want to say that one of the things that I've been involved with that you might want to consider is, as you're trying to get people to understand the scope of the issue, according to federal data, every Canadian household emits 4,200 kilograms per year of carbon. That works out to 6 pounds per square foot. So depending on whether you like metric or you like imperial, blah, blah, blah. But I've always found that with presentations, people can understand that, 6 pounds per square foot, that's what my household dirt is that I have to clean up. The only point I did want to take exception to in your presentation, when you were talking about increase of renewables as an offset, I've been arguing against this for ages, that if we were to make free solar and wind and energy, nuclear, whatever the source is, became absolutely infinitely free, that would have huge, very profound and unpredicted consequences on our planet, as in we would deplete our resources and destroy our planet, not from an environmental point of view, but from a resource point of view. So I always hesitate to say, let's just increase renewables, until I've said, let's decrease our consumption and decrease it to the absolute minimum. Then the absolute minimum should be met with renewables as a supply option.
Well, the list of things that what you can do or what can happen is quite long. And renewables are just one part of that list. So, but I agree with you. The whole business with lithium and copper and cobalt and nickel and whatever have you, they're happening questions right now. So it's not just renewables.
Thanks, David and Bill. And I think this is a very, this is the right way to leave this conversation off. It is not just renewable are just part of the equation, and one aspect of how we can be more aware about how our activities impact the climate. So thank you again, David, and everybody who took out time from their day to attend the presentation today. We will be posting the recording of the presentation on our website, and we will also let you guys know once the recording is up on the website. Thanks, everyone. Have a good rest of your week.
Thank you very much.